10 a.m., so I'll start in a sec. To anyone who's joined since then, feel free to at me or, pop up in voice chat if you have a question. But keep in mind, this seminar is kind of assuming you know some basic QFT, and I'm assuming...
I know nothing.
I'm assuming, I guess you've seen some of the previous... either you know some basic QFT, or you've seen some of the previous seminars in this series. Yeah. So, anything anyone want to chime in before we begin?
Yeah, yo mama.
Ooh, tell that to the physics Discord. Oh, wait. All right, cool.
Wow.
So, today I'll be talking about quantum chromodynamics and lattice quantum chromodynamics. And by that, I mean, what I really mean is I'll be describing quantum chromodynamics for the most part. And I will be describing some of the naive approaches to lattice quantum chromodynamics.
I have a question.
Yes.
Is there any relation between statistical mechanics and this stuff? Sorry if it's a bit of a stupid question.
Sure. I mean, a quantum chromodynamics itself, no, but the lattice QCD bit, a lot of the same techniques are used in doing simulations of, ensembles of particles.
Right. I see. Sounds cool. Thank you.
You're welcome. Okay. So, first, why believe in QCD in the first place? There are a variety of reasons. I just cherry-picked some, such as the proton and neutron have larger magnetic moments than expected. Some scattering experiments with high-energy electron scatterings suggest 3 localized particles inside protons and neutrons, and a variety of other things. So, if you know anything about quantum chromodynamics, you know it's a theory that describes 6 quarks, which with 3 colors, whatever color means. So first, why 3 colors? Well, here's a little picture on the left, and it shows a picture of the proton with 2 up quarks and a down quark, composing it. And people said, oh, well, these 2 up quarks are in the proton, so they must be, in the same state because they seem to be symmetric. Like, symmetrically compose the proton. But we know quarks are spin 1/2 particles. They're fermions. And so we know that 2 fermions can't be in the same state. So that, among that and other reasons, people, specifically Oscar Greenberg, proposed 3 different colors that quarks can have. Color being a quantum number. Kind of like, another spin, except there are 3 of them you can have. However, one thing I didn't really see, so in case anyone knows the answer to this, why couldn't we instead have a proton, say, with an up spin, be composed of 2 up quarks with opposite spins, and then a down quark of, say, up spin?
Wouldn't it have negative charge? Oh, sorry. No, it won't. Sorry.
No. Also, it's too bad. I don't know if Hankel ended up joining. That's okay. That means I can skip my optional slides.
Oh, they're here.
Wouldn't it be 1/2 spin? Like it would only be half charge, not charge.
I mean, it would have the right charge, and it would have 1/2 spin, which is approximately what we observe.
Oh wait, hold on. Does down up mean it's anti-down?
No, these are all regular particles, not
Okay.
antiparticles.
What's the answer then?
Oh, I don't know. It was a legit question.
Oh, okay.
So, on the other hand, why 6 quarks in the first place? So, to answer that, I'll talk about the results of one particular kind of experiment, which is you throw an electron and a positron together at high energy, and this process then has a total energy of E. And they'll annihilate, and they'll spray a shower of decay products like photons and particle pairs like muon, anti-muon pairs, quark, anti-quark pairs, etc. And the thing is, these quark, anti-quark pairs that result will form baryons, which are just, bound states of multiple quarks. And so you can take these two processes, the muon, anti-muon observations you get versus the quark, anti-quark, like the baryon content you see in the experiment, and you can take that ratio of how many of this event do you see versus this event. And if there are a ton of different kinds of quarks, you will see a higher ratio of these decay products versus the muon anti-muon pairs. So people have done experiments like this. And so this is this ratio on the vertical axis versus the energy of the electron-positron pair on the horizontal axis. And the bottom line is what you would expect if you had a 5-quark standard model, but they only had one color. And you can see this line is way below the experimental data points. The experimental data points are closest to this model of 5 quarks with 3 colors. So meaning the positron-electron pairs are, the annihilation is producing decay products that are ended up being formed out of 5 quarks of 3 different colors. And you say, well, we know there are 6 quarks, so what's the problem? The thing is, this graph isn't plotting things at high enough energy. It turns out the top quark is of higher energy than this process going on. As you can see, there's even a bit of an upturn near the higher end of the energy of this plot, closer to the 6 quark 3 color line. And more recent experiments have, of course, confirmed the existence of the top quark.
Is the sigma the cross section?
Basically, yeah. It's basically this ratio of baryon content observed versus muon content observed in the decay products.
Right. Okay.
So yeah, it's the ratio of cross sections. So now I'll describe a bit of QCD, and unfortunately there are much less pictures. So first, as in any field theory, first we'd like to describe the classical action. So very similar to what Uzu did last week with QED, we'd like to start with a purely fermionic action. So we know there are 6 quarks of 3 colors. So this action, which is the energy roughly of your configurations, is going to be a bilinear operator in your fermions fields, where these indices. F are for flavor, meaning, up, down, strange quarks, and color. Red, blue, green is the convention we use. And so this looks basically exactly like the QED action, which I will assume you've seen before for the purposes of this talk, since the QED seminar was last week for the series.
I have a question.
Yes.
What is the purpose of summing and doing an integral or something?
Well, we're summing over indices and we're integrating over space.
Oh, okay, I get you.
So these size depend on the flavor, color, and the space-time index.
I have a question too. So
Sure.
this is basically from the Klein-Gordon equation, the operator in the middle.
Well, you have
the Dirac equation.
Yeah, it's basically like the Dirac equation, the operator in the middle.
And the D contains an vector field A?
Yes, I'll get to that.
Okay.
But yes, this is not just the regular derivative. This is the covariant derivative. And so to give you a little more idea, in QED, the states are really spinors, where this psi f QED state has 4 components for each flavor. So the flavors in QED are really the electron, muon, or tau. So 4 components here, but 3 different flavors for QED. So
what's the difference between the wave functions with a bar on top and not?
So in this description, the bars are antiparticles, and the ones without bars are regular particles.
Okay, I get you.
But the convention here in this description is slightly different from the convention used in the action that I've written down, where here the bar is kind of denoting a Hermitian conjugate. So in QCD, the fermion fields have the exact same structure, except you now have a color label associated as well. So each of these objects with a C index are themselves 3 color component objects. And for an example, here's the strange quark written down. I've just expanded what I was showing before, but I've written out, the fact that we have 3 colors for each of these 4 components.
Each of them is a scalar, right? Like each coordinate. Just one dimensional.
Yeah, a scalar depending on the space-time index.
Yeah.
Yeah. So, well, if we're talking about Lorentz invariance, if we're talking about scalars in terms of Lorentz invariance, then no, they are not scalars. They are components of spinors. But I suspect that is different from. All right.
Okay. Cool.
So, as I said before, we start with a fermionic action, and we try to apply gauge invariance, meaning, as you know from QED, if you try to apply a local gauge invariant transformation to the fields, the action should be the same. And so very similar to QED, which I won't go into since I'm assuming you saw last week's talk. Very similar to QED, you see that gauge invariance tells you that this covariant derivative is the regular derivative plus an extra component that depends on your space-time index, as well as C and D, which here are color indices. So the C and D dependence, I'll absorb into this tilde and just say that this A mu is a matrix that depends on space-time position, or space-time location. And this A tilde mu object under a gauge transformation should transform in this way. You have a n by n color rotation matrix that can switch between the components, the color components of this A mu operator. And this color matrix can depend on the space-time location that we're talking about for the transformation. So, different from QED, where here you just had an A mu of X, here we have additional color degrees of freedom, which is why this A mu is more complicated. So these color rotation matrices, since their determinant is 1, we say they're in the SU of NC group. And it's very useful to build these matrices with the generators of this group, basically to ensure that the determinant relation is always maintained, and for a few other good computational reasons. Okay. So, as a reminder, here's this covariant derivative, and very similar to QED, you construct the field strength tensor by basically taking the commutator of your covariant derivatives. That ensures that this object can also be used to build gauge invariant scalars. So the complication here is that due to these additional color degrees of freedom, this commutator between A mu and A nu does not vanish. And here on the right, I've expressed this F mu nu in terms of the generators of SU NC. The color group, I'll probably call it for now. And then very similar to QED, we allow this F mu nu to dynamically fluctuate. And so, just like in QED, the action for the gauge fields has this F mu nu form. But now we also want to trace over the color degrees of freedom here. Note that this F mu nu has color degrees of freedom because these A mus are matrices in color space. So here, this is just the convention of how to write the coupling 1 over 2g squared. And instead of writing the trace over color degrees of freedom every time, I'm just going to use Einstein's summation convention. And by convention, the source I was following also changes this prefactor. Okay. So
the indices should be kind of flipped, right? Like upside down, like for mu nu, like the indices, like mu nu should be, one should be below and like another should be above, right? In the last line on the right.
Normally I'd agree with you, but the source I was following didn't have that. And
the cutoff, it seems like it should be like does anyone have like a correct answer to this in the audience?
Yeah, so whenever you're taking like contravariant, contractions, basically what you're doing is that you're doing a contraction against the metric, right?
Right.
So if you have like your spatial manifold, it's a Riemannian or pseudo-Riemannian or whatever. Whenever you put these like two tensors together, right? That's what you have to do. You have to contract the metric, but I'm assuming that we're working with like flat space and Euclidean space.
Yeah.
Right? So like if it's Euclidean, right?
Oh,
Then,
I see. Yes.
so if it's
The
Euclidean,
convention is that. Thank you for the reminder.
Yeah.
The convention in lattice QCD is to work in Euclidean space.
Exactly.
And so this description of QCD is really relevant for Euclidean space, which means you don't need to worry about covariant, contravariant contractions because the metric is just all ones. To motivate the trace, okay. Let's see. So, well, in some sense, the trace over colors is very similar to your trace over the contraction over the mu news here. We want our action itself to be a scalar. So we want to take the trace over in color space, but you're right, there could be some other options. Instead of taking a trace, you could take like an element-wise product and add those objects. And admittedly, I'm not sure why the trace itself is used. I suspect it's to make. I suspect it's just because the trace is going to be invariant under these SU3 color rotations. Yeah, Hank, as you're mentioning, it's for gauge invariance as well as this color rotation invariance. Yep. Okay. So for quantum chromodynamics, I'll check in the chat periodically. For quantum chromodynamics, what we do is we take the classical action we've been building and we construct a path integral. Here's, for example, the vacuum amplitude. And here I'm a little inconsistent because I'm writing this as if I were working in Minkowski space because I have an e to the is. But in reality, for the lattice QCD stuff, I've been building the rest of this in Euclidean space. And I'll show later a wick rotation. So the action we've been building has this form. You have the fermions with the gauge fields in the d mu, and you have the gauge field action here. So I have some optional slides about other allowed terms in the action. And so I can either skip these now, get back to these later, or I can go through them now. They're basically saying, despite this being the simplest possible action in quantum chromodynamics, there are other allowed actions that have some motivation behind them. But it's a fairly technical tangent. So I'll skip this optional stuff for now, and if we have time later, I'll go through it. It's basically talking about the theta term that Hankel was so interested in. Okay, so QCD is pretty fancy, right? But there are some things that you can't do with it. For example, QCD is a strongly coupled theory.
What's coupled in the theory?
What's coupled in the theory? The fact that this d mu has the gauge field A inside of it, which is used to construct these Fs, mean that the quarks here are coupled to the gauge fields here, which I'll start referring to as gluons. So
Okay.
if you like, the bits that go into D are connected with the bits that go into F.
I see. Thank you.
Which leads to the coupling. Another thing that I'll point out is that because this F mu nu still has this commutator of the A's here present, the bilinear in F mu nu, so this product of 2 leads actually to 4 A's in the action, which means that you now have gluons interacting with themselves. So the gluons are interacting with themselves, not just the quarks. And that's a non-trivial difference from quantum electrodynamics, where the photons don't interact among themselves. They only interact with, electrons or other charged particles. So that's another reason why this is a strongly coupled theory. And so perturbation theory doesn't really work. It kind of works for extremely high energies because QCD is what's called asymptotically free. And as you lower the energy scale that you care about describing, the QCD coupling constant increases. And this is related to the renormalization group that someone was asking about before we began. So low energy properties of your system, such as confinement of quarks, confinement into nuclei or pions and other mesons, are pretty much out of reach in perturbation theory. There are fancy techniques one can use to try and, extract non-perturbative information out of an asymptotic perturbative series, such as Borel resummation and Pade approximants, but even these techniques fail for QCD. Yeah, Hank, if we have time, or if you ask questions, I'll go back to those slides. Uzu, what does strong coupling mean here? What this means is that this G squared here is on the order of 1. Okay, so there are actually 2 things. One is that this G squared is on the order of 1, whereas for QED, your coupling constant is kind of the alpha, the fine structure constant, 1 over 137. And the other difference is that these gluons are interacting amongst themselves because of what I mentioned before, which is different from photons, which don't interact among themselves. So that leads to non-trivial interactions that make it much harder to study the quark content of the theory.
Thanks.
Yeah, you're welcome. Feel free to follow up. Okay, so let's talk a bit about lattice QCD now. And first we'll warm up with some lattice scalar field theory. So first I'll mention the wick rotation that's going to happen. Basically, we blindly make the substitution t equals I tau to go to imaginary time, so that instead of writing e to the is in our path integral, it's e to the minus s. So it turns this very oscillatory path integral into an exponentially peaked one, so long as s is positive definite, which is something you have to keep track of. And sometimes to ensure that, you have to use fancy techniques to analyze this action, which I won't go into here. So this is a tangent into scalar field theory, just to develop some of the computational tools that go into lattice QCD. And note that a scalar field theory is kind of what describes the Higgs boson. And it has this action. You have a mass term, your gradient squared, and a potential v of phi. And for those of you who like the renormalization group, we typically take this potential to be phi to the fourth, since higher powers end up being irrelevant for space-time dimensions greater than or equal to 4. And Minkowski space is d equals to 4. And as a reminder, this is the atypical observable, a single particle correlation function, and you might compute it in the path integral by computing this quantity. Z is the path integral over e to the minus s. And what you do is, this is one of the moments with respect to phi of this path integral. So this should all be a review. And so for doing simulations, you choose a lattice. And while this technically breaks, some of the symmetries of space-time, what we're most worried about usually is respecting gauge invariance, and we'll have to talk about that later. So on a lattice, the action ends up being discretized. So we have to discretize the action, which means that these derivatives get turned into, finite difference schemes. So for a finite lattice discretization A, this is what the action ends up looking like. You have your finite difference approximation to the derivative here. You have a mass term again, and your potential. Okay. So one of the things that is worrying about a discretization like this is that, say we look at the case where we have no potential and no mass. The correlation function we were talking about earlier looks like 1 over a squared, 1 minus cosine of k times your lattice spacing, which has this form, k squared times other bits. And the thing is, ideally, we want to get to the continuum limit. So we want to take a goes to 0. But the problem is, our first correction is of the order of a squared. And the question is, can we use any tricks to make this a squared term disappear and the error in a, make the error in a get put into higher order terms in this ellipsis? So one of the tricks used to improve this situation is, instead of using the naive forward difference approximation, we can use convex combinations of higher order differences that eliminate higher order terms in A from this use case. So, for example, if we use an approximation to the derivative that looks like this, then this ends up being more accurate for a finite lattice spacing. So, for example, one of the first improvements, this is called a Symanzik improvement. You end up getting a correlation function in momentum space that is proportional to k squared plus bits of order a to the fourth instead of a squared above. So that's already a good improvement. Uzu. Yeah, it's the 2-point correlator, which is what I'm calling the one single particle correlation function.
So that's G, right?
Yeah.
Thanks.
Yeah. So if you look at the definition here, you can orient yourself. So yeah, what Uzu is saying is this is the 2-point correlator because we have a phi of x and a phi of x prime moment here in this functional integral. But typically, single particle correlation functions are 2-point correlators. Okay. So, if we wanted to do quantum Monte Carlo of scalar field theory, note that the goal is to evaluate this functional integral. The most naive thing
What's
you
Z?
could Z is this integral without the phi of x prime out in front.
Oh, okay. I see.
Yep. So if you like, it's the normalization, or some people call it the partition function.
I'm
if you
using the
like.
partition function A.
Yeah. So the most naive thing you could do for numerically evaluating this functional integral is generate a random set of configurations, so field configurations phi n of x, and basically evaluate this using Riemann sums. Of course, it's infinite dimensional Riemann sums, but here's a picture I drew where the horizontal axis is this exponential of the minus action, and the horizontal axis is a cartoon of the configuration space for phi. Since this is an exponential, we know it's going to be highly peaked. Maybe it has a couple of peaks near its minimum. And if we uniformly sample the configurations phi, you can see we're doing an awesome job of, sampling the space. We're totally going to get this right. If you can't tell, that was sarcasm. Uniform sampling is a terrible idea for integrating functions that are highly peaked in a certain region. Uzu, the Euclidean signature, the main importance of the Euclidean signature is to ensure that the action has it looks like e to the minus s out here, which means this function is exponentially localized around a particular phi value.
Okay.
Yeah, if we were working in Minkowski space, this would be an e to the is, which would be oscillatory. And numerical calculations, trying to calculate an oscillatory integral is very difficult.
Right. Okay.
Yeah, you can discretize Minkowski.
Yeah, but can it be done in like those cubical pieces as well? Like, it's just kind of throwing my intuition at it. I think just
Sure. I mean,
yeah. I guess
There's-
it's fine. Yeah.
there'd be nothing wrong with that, except
Okay.
computing power.
Yeah. I was. Yeah. Okay.
Let's see. So pugs, the 5x prime here makes this not the partition function. The partition function would be this functional integral without the additional 5x prime powers. Okay, so we've talked about how uniform sampling is really bad, right? Can we do better? The answer
Question.
is of course. Oh, sure. What's up?
Do the 3 peaks represent the 3 main colors RGB?
No, this is just a cartoon.
Okay, that was just a wild guess.
No, it's a decent guess, actually, but no. I could have drawn just one peak, but there are cases where there are multiple peaks in this integrand. But no, it's unrelated to the colors at this point.
Yeah, I just read the title of the slide, and I guess that makes sense. It's not really to do with QCD, it's scalar field theory.
Right. So we can do better. Instead of uniform sampling, we will sample the configurations phi using the Metropolis approach, where we start with a configuration here in orange. It's a random configuration, so it might be really bad, might be booty. But what you do is you do a weighted Metropolis sampling. I'll explain what that is in the next slide, but for now, what we do is we start in a random configuration, and we update our configuration by looking at whether or not we get closer to the peak of this function. If we get closer to the peak of this function, then we will accept the step. And so our configuration starts here, and in a few steps, we are sampling the peak or peaks of this function. And the weighted Metropolis sampling algorithm ensures that we primarily sample this peaked region. So what exactly goes into this Metropolis approach? First, as I said, you start with a randomly generated field configuration. And recall this is on a lattice, so we have a finite number of degrees of freedom for a given field. At a given lattice site, we will randomly suggest the value of the field, the value of this function, to change at that lattice site. Then we make the Metropolis choice. If the change in the action resulting from this change in phi is negative, or if we make this comparison, exponential of minus beta change in action is less than r, where r is a random number. For either of those two cases, we accept the change, otherwise reject it. The reasoning behind this step is that if we only accepted changes where the action were negative, then we would just be doing a search for the classical minimum of the action S. But as you all know, quantum mechanics is not classical mechanics, and so we have to have a way of introducing fluctuations into the system. And so that's why this next comparison is here. If the change to the action isn't too large, given this parameter beta, if the change in this action isn't too large, then let's see, then this quantity will be reasonable, and this comparison will allow us to allow the fluctuation to happen in our system. So in this case, the quantum fluctuation. Right. So we are seeing the Metropolis sampling happen. We can account for quantum fluctuations. The same algorithm can be used for anything, not just lattice field theory. We can do this for statistical mechanical systems if we wanted. Next, in step 4, we sweep through all the lattice sites doing the same thing to generate a new field configuration. Then, at the end, we might make a measurement of observables using this new field configuration. We repeat from step 2, and we accumulate these measurements to build expectation values. Right, so it's a fairly complex procedure, but what it allows us to do is do exactly what this picture suggests. Even if we start off in a bad configuration, we end up sampling heavily the peak in the of the integrand here. Any questions so far?
I have a short question.
What's up?
So, is R like chosen really randomly, or like are we looking for small values of R, like 0.001 or whatever? Like it seemed like you wanted to do more sampling in the peaks.
So depending on your problem, this is a parameter you can tune.
Right. It's
Naively,
not really a random number. It's more like
oh, sorry. The R is selected to be a
Right.
random number during each step. It's this beta that's the parameter you can tune. The R is a truly random number.
Oh, okay. Okay. I don't think I'll understand like the thorough details, but like please go on.
Sure. The reasoning for this being a random number is essentially, I won't go into the details, but it's essentially to satisfy what's called detailed balance, meaning the likelihood of you fluctuating the field in one way is equal to the likelihood of you relaxing from that fluctuation. So it's kind of like an equilibrium idea. And so that's why this parameter is random instead of being a fixed value like 0.5. I'll move on then. So now let's start talking about actual fermions, because scalar field theory is a theory of scalar particles. But we're interested in fermions. So one problem is that in reality, if you know some basic QFT, you'll know that fermions cannot actually be represented by real numbers in this path integral. The anti-symmetric property of the fermion creation annihilation operators, or just the anti-commutativity property, or the anti-symmetry of fermions in wave functions, however you want to view it, fermions are more complicated than real numbers. So I won't go into the details, since I'm assuming, again that you've seen some basic QFT, but what makes this complicated, this lattice quantum Monte Carlo approach for fermions complicated, is the fact that these psi's are Grassmann valued. So we would like to get rid of these Grassmann numbers, if possible. physicists hate them. So we use the Grassmann integration rules that you learn in a basic QFT course to integrate them out, which is something we can do if we have a Gaussian Grassmann integral. And so for QCD, the fermions only appear in this bilinear expression, right? Same as QED. So what that means is that since there are only two fermion fields here and here, this integral ends up being a Gaussian integral, and we can use the fermionic Grassmann integration properties to get rid of them. So if we perform this integration over the fermions, what that leaves us with is a theory purely of gluons. So here's the effective action after integrating out fermions. What you have to do, if you don't remember the integration rule for fermions, is that you take this operator, gamma mu d mu plus m, and you calculate this integral by bringing down this determinant of this operator. Now, what makes this complicated is that this determinant isn't just a number for the purposes of this integral. Remember, this covariant derivative has this gauge field A in it. We can do some manipulations to write our partition function with an effective action, where the effective action is our usual gluon action minus the trace of the log of this operator. This is just using some operators or some relations that you would see in a basic QFT class. Determinant of a matrix is e to the log of the determinants, etc. So here I remind you of the structure of this covariant derivative.
Brief question, because this appears recurs. Is the a tilde equal to the a? Like, what is the difference between like you putting a tilde and a?
Sorry, that's inconsistent notation on my part. Pretend that everywhere is a tilde, where a tilde is this matrix over color indices. So really, this integration should be over a tilde. This should be a tilde. This should be a tilde.
So
this should be
a tilde like 4/3, where like 4 is Lorentz and like 3 is color.
It's going to be 4 Lorentz components. Each of those Lorentz components is a 3×3 matrix.
Oh, okay. So it's like 4×3×3, kind of.
Kind of, yeah.
And like you also don't put the coupling strength there. Shouldn't it be like IGA or something? Or is it just absorbed in, I guess, or something?
The coupling constant would be, if you're talking about the coupling constant of the gauge fields.
Yeah. Gauge derivative.
In the gauge derivative, that's it is of this form without an extra coupling constant, I believe, but maybe I'm wrong about that.
Because in QED, you should have like IQA, where Q is your coupling constant charge. And
you're right.
I think like maybe this one is like absorbed in either that or like there's a typo. So
yeah, this is what my source was writing. So let's just say it's absorbed in it.
Okay, cool.
I believe actually what it is the no, I can't say for sure. Maybe the chat will have an idea, but my guess is that in QCD we actually treat the coupling as 1 here. Okay, so to summarize so far, we're wanting to do QCD computationally, non-perturbatively, and QCD involves fermions, which we would like to get rid of because Grassmann objects are hard to deal with computationally. So we integrate out the fermions using analytic techniques that you see in a basic QFT course. And now we have a QCD action purely with the gluons, the gauge fields. One of the computational problems is needing to compute this trace log here. So one of the computational problems is efficiently computing the logarithm of this operator, because remember, this M is really a mass matrix, this D is really an operator, and so computing the logarithm of this and then the trace of that can be demanding, especially considering this, in theory, is infinite dimensional. But on a lattice, it's finite dimensional. Let's see. So, one of my questions to the audience, if anyone knows, is that the approach that I'm pushing for right now has you entirely integrating out the fermions. And just looking at possibly doing numerics on this effective gluon integral. But lattice QCD, the approaches I've been seeing have a lot of worries about, the properties of the fermions and the discretization of the fermions on the lattice. But in what I've been doing here, I have done all these manipulations technically in the continuum. I haven't discretized these objects yet. So my question is, why can't we just discretize this in the gluons and not have to worry about the fermion discretization problems that typically pop up in QCD? Some thoughts that I had were, one, maybe it's inconsistent to integrate out the fermions exactly in the continuum sense, but treat the gluons on a discrete lattice. Or two, maybe we have to worry about how to account for the quantum chiral anomaly if we were to just naively discretize this gluonic action. Great. So we've talked about, putting QCD onto a computer, some of the steps that we need to do. Let's talk about more steps. We'd like to discretize this integral over the gluons, but we'd like to do it in a gauge invariant way. Let's see. This comment only makes sense. You can ignore this theta term for now. So we'd like to discretize the gluon fields. Here's a motivating example. Imagine you're integrating a vector function over an area A here on the left. And let's imagine that this function can be written as the curl of some other vector function. So that if we were to perform this integral, it really looks like this integral. By Stokes' theorem, you can compute this integral over the area by performing an integral over the boundary of this area. Right, and that's why I have the arrows here. I'm choosing a direction for the surface integral. In this case, it's a line integral. Yeah. So what we could do instead of performing this surface or line integral around this area, we could break up this area into a bunch of different smaller domains. And why should we do this? Well, the integral over this area should be equal to the integral over, the sum, or the sum of the integrals over these areas. But if we were to break up each of these areas, we should be able to apply Stokes' theorem for computing this integral on each of these smaller areas. Right? And if we add up those contributions, we should get the same integral, because we've done nothing other than draw a couple lines. We haven't really changed the integral. But Slendergandel, you say, we're doing extra work. You see, we're computing 9 line integrals here instead of 1 line integral. Well, you can note something, which is that if you look at this outline here that I've pointed out, these integrals, the leftward contribution of this A2 and the rightward contribution of this A5 here for this part of the surface, these two contributions will cancel since they're integrating over the same line but in different directions. And so this is an easy way to see that the two integrations, even after using Stokes' theorem, are the same. And so what we're going to do is we're going to define the surface of each of these areas. So each of these, squares, we're going to define as a plaquette, piece of I.
I have a question.
Yes.
What's the infinitesimal upside down L thing? The D upside down L in the UI equals closed surface integral P of I, the equation. Yeah, that one. The upside down L on the right.
Gamma.
That's
so
gamma? What?
D gamma.
Is that
capital gamma?
Oh, I didn't know that. That's cool. Thanks.
No problem. So
what's it meant to represent as well?
So basically, if you treat the I'm writing D gamma as the line element along the surface here.
Okay, I see.
Or along the perimeter here. So we're going to define this sub little area Stokes integral. Say for A5, it would be U5 equals the line integral around the area of A5, around the perimeter of A5 of this function dotted with the line element D gamma around here. So I've drawn you some pictures. Our original integral should then be equal to the sum of these UIs over the plaquettes, or over the boundaries here. Any questions about what I've drawn here?
Nope.
Okay, so we've done this for a very basic, example of integrating a function. And what we've done is we've written this integral over an area into a sum over surfaces or perimeters here. And I'm going to call these plaquettes. Now, why is this important? Well, it turns out that for discretizing the gluon action, we can do a very similar thing. I won't go into the details of why it's similar, or how it actually works. They're much more skilled people than me that can do that. But I'll just say it is similar with lattice QCD gluon fields. If we define a function like this, here's some path ordering and exponential, and here's this integral over a line path of our a mu gluon field. So if you like, we might be integrating this over this area path. We are defining this in terms of two endpoints, x and y. So this is a slightly more general object than what I was showing you. So that u of x, y might be this integration from, say, this corner to across to this corner and to this corner. So this one might be x, and you might integrate this quantity over to y. If we define the object u, x, y like that, then next we're going to define u mu of x as this above object, but where the second argument is x plus this unit vector in the mu direction. And so plugging in this above definition here, it looks like this. You know, it's the same thing as this, but we replace y with x plus mu. And we notice that if the spacing between x and mu is small, then we can approximate this integral by the midpoint of the integrand. Yeah. Next, I'll define this u mu nu, which is the product of four of these objects: u mu, u nu, u mu dagger, u nu dagger. Basically, what this u mu nu is this full object defined by integrating, say, from this corner to the left in the mu direction, to up in the nu direction, to the right in the mu direction, and down in the nu direction. So it's basically, I'm just using slightly fancier definitions to do the same exact thing as I was doing before, which is defining an object that lives on the space of this loop. And you'll note that if you plug these four objects together using this definition, you end up getting f mu nu, actually, constructed from these a mu's by approximating the by using some finite difference finite difference derivative definitions. You get an a squared f mu nu of x plus larger terms in a cubed and higher. So the reason I emphasize this definition, this dependence on a, is because if you remember, the lattice spacing is going to be a. And so we want to take that to the continuum limit to a goes to 0, which means that as a goes to 0, this exponential is approximately equal to 1 plus ia squared, f mu nu of x minus a to the fourth over 2 f mu nu squared plus higher order terms in A. Any questions so far? Let's see chat. Yeah. You can see that they satisfy what Hank is saying in the chat by just looking at the definition. If you take the complex conjugate, you switch the sign of the I here, which is similar to reversing the direction of integration, because If you make a minus sign here, that's the same thing as flipping the upper and lower bounds in an integral. Okay, this seems like a lot of work to define some objects for what seems to be no good reason. Well, the thing is we can use, because these u mu nus are 1 plus an imaginary bit minus f mu nu squared times a to the 4th. If you recall, our original action involved f mu nu squared. So what we can do is use these u mu nus to construct a discretized action. And this is called the Wilson gauge action or the plaquette action. If you take the trace of 1 minus u mu nu of x and you take the real part, you'll see that taking 1 minus this gets rid of this 1, the real part gets rid of this I, and you're left with an f mu nu squared. So I won't bore you with the details, but if you make the comparison between this discrete action, then as a goes to 0, this Wilson action has this form, and as a goes to 0, this leads to your usual continuum limit of the action for the gluons. Now, the reason we did all this work is that this formulation is actually gauge invariant. This is a gauge invariant way of discretizing the gauge fields on your lattice. And so that's very important because, we want to preserve gauge invariance in our theory. And so we want to preserve it on our computer as well. Okay. So we're almost to the end of what I wanted to tell you about. Because to go further would be even harder on the brain, I would think. I'll just mention that with this change of variables to these plaquettes, instead of writing our partition function or our vacuum amplitude as the functional integral over the gauge field A, we can actually write it as I'm just using the same notation, as a integral over the plaquettes U, with a much reduced configuration space. Furthermore, if we want to apply the Metropolis algorithm or other algorithms to performing this integral, we can randomly generate these links from the generators of the group algebra for the gauge fields without actually computing a gauge field A first and then doing that exponential of the integral of A's. One of the problems with doing this, though, the problem with entirely getting rid of your gauge fields in favor of the links here, or the plaquettes, is that some observables are very difficult to represent in this plaquette basis. You can compute some things like the Wilson loop observable, which is basically the expectation value of one of these plaquettes. But getting fermion properties, for example, out of this is much harder once you've made this change of variables to the plaquettes. But on the positive side, again, you can actually randomly generate these U's and be much more computationally efficient than working directly with these FMU fields. So the last thing I have is a movie. So here I'm showing a movie available on YouTube of someone else doing a lattice QCD calculation. Here's the energy density. They're doing lattice QCD in a box that is big enough to hold about 2 protons. And so here's the energy density of, well, now here's an electric field. And I'll just let you see the pretty pictures. And while this is running, does anyone have any questions or comments?
What are those little fluctuations in the field?
Well, right now it's plotting, well, it was plotting electric fields, now it's plotting chromomagnetic fields. So the fluctuations, I don't know of a good way to describe them, to be honest.
Okay.
When they were plotting the energy density a minute
It's
ago.
just like a 3D vector field, right?
Yeah, this is just a 3D vector field that they're plotting. I can tell you that when they were plotting the energy density was the fluctuations.
For example, the big red arrow, does that mean?
The bigger and redder the arrow, the larger is the component of the vector field.
Okay. Yep.
I'm not like are you done, or like is there more stuff?
This is the last slide, unless Hank wants to talk about the theta term that I have in some previous slides, or if anyone else wants to.
Well, why don't we give you an applause anyway? Like, I think it's
Yeah.
customary and it's good, I think.
Thank you.
Yep, it works. You can hear me well. I'm clapping for you as well.
Thank you.
I think I'm the only one who clapped or something, which is a little sad, but okay.
It's more sad when you point it out, man. No, I'm just kidding.
Indeed is. But I actually want to know, because you see, the thing about the last QCD video that you were showing is, I mean, I saw that video before and like I thought it's really cool, but I am not entirely sure like how these like really link back to a lot of calculations you did before. In that, like, I can see that like each vector there is like a gluon field, or the quark field, which would be given by like little spinners and stuff. So it makes sense that there are like little vector fields fluctuating over time. But how exactly is this calculation obtained from like what you wrote before? Because I remember you were trying to approximate the propagators and not exactly like point-wise what's going on and so on, like, for which I mostly lost the details.
Yeah, fair enough. So I can say that for the energy density, and here they're computing the part of that movie, they were also computing the topological charge density. For those quantities, you can more easily represent the energy density and the topological charge density in terms of these plaquettes. And so what they do is well, admittedly, I don't know the details of how these folks specifically did this calculation, but if you were to go with the approach that I've been talking about, then you can map observables like the energy density and the topological charge density into this plaquette space and do this computation, not just for z, but you insert an observable here in the functional integral, like the energy density, it expressed in terms of these u variables. And then you can compute it and you can plot it over time. And that's what they were doing here. For the electro and magnetic...
Actually, most of the voice cut out for me, like because of the connection problem, one way or another. So
well, to answer your question again in a short manner, if they were doing the calculation along the lines of what I had been telling you about, then what they did is they expressed the energy density, the topological charge density, etc., in terms of the u variables. And they inserted those observables here in this functional integral. And they used the Metropolis algorithm to integrate basically over the u's.
Yeah, so I do want to talk about the chiral anomaly, but I just wanted to know what you have, like the slides that you have. Yeah.
So we can look at them.
Sure.
So I'll just go through what I was planning on then.
Yeah.
Technically, even though this is the simplest QCD action you could have, if we look at the gluon action, you'll see there's a trace of mu nu, and color indices. These are generator indices for the SU3 group, actually. You could have an additional interaction, theta times this integral, where you have an anti-symmetric tensor, mu nu rho sigma, mu nu rho sigma of the f's here.
Mm-hmm.
And this theta term would violate C and CP symmetries unless the mass of quarks is 0. But the thing is, the fact that our quarks have non-zero mass means the chiral symmetry is already broken anyway in QCD. So what that means is that there's no a priori reason to exclude a theta term like this. And what I was going to go into is saying that a theta term is already effectively generated due to the chiral quantum anomaly in the path integral. And so the chiral quantum anomaly is basically when a quantum anomaly in of itself is when the action is invariant under a transformation, but the measure of the path integral is not invariant under the transformation. And so if we assume the fermions are massless, if we perform this chiral gauge transformation, the action is invariant. Of course, we know that the masses are non-zero, but we expect Goldstone or pseudo-Goldstone modes from this symmetry breaking by adding masses by breaking this chiral symmetry. But the thing is, some of these particles that are these Goldstone or pseudo-Goldstone modes have too large of a mass to actually be pseudo-Goldstone modes. The key to understanding this is in understanding the chiral anomaly. And so here I'm going into what the measure looks like, the change in the measure when you perform an infinitesimal chiral U1 transformation. And so if you regularize the Jacobian in a gauge invariant way, then the change in the measure ends up looking like this, where this fancy A is expressed in terms of this antisymmetric combination of the F mu nu rho sigma terms. Yeah.
What's alpha F?
Let's see. Alpha F would be just an arbitrary parameter in this infinitesimal gauge transformation. Infinitesimal chiral gauge transformation. So alpha F in principle is arbitrary. It's just infinitesimal in order to derive this specific form.
Okay.
It's an arbitrary scalar that is infinitesimal in order to derive this particular form. And
yeah,
noting
what I was gonna say is like right next. In the next step. So yeah, no, keep going. This is good.
Thank you. Yeah. So yeah, the fact that this change in the measure occurs with this form, you'll notice you can absorb this exponential form into the e to the is itself for the action, which ends up looking the same as changing your QCD Lagrangian into the QCD Lagrangian minus this Chern Pontryagin.
Yeah.
And you'll notice this form is exactly the same form as this theta term that I showed up here. So this quantum anomaly actually ends up contributing an effective theta term to the integral anyway. I'm pulling this stuff from various sections and chapters in Weinberg Volume 2, by the way. So if we kind of want this chiral anomaly because the particles we observe are too massive to be the result of this spontaneous chiral symmetry breaking with light quark masses. So we want this chiral anomaly to be non-zero, it turns out. But the thing is, this action is a highly antisymmetric object. You know, you've got the totally antisymmetric tensor here. You have antisymmetric quantities. It could be that this action is just vanishes identically for any physically relevant gauge configurations. But I won't go through it, but it turns out, and here are the relevant sections of Weinberg, they're topologically non-trivial configurations that make this term finite, and therefore give a measurable, or at least a finite contribution to the chiral symmetry, or the quantum chiral anomaly. And so this quantum chiral anomaly provides an extra chiral U1 symmetry breaking term in our theory. And since the chiral symmetry is broken more, we can kind of justify the fact that some of the particles we expect from this chiral symmetry breaking are actually more massive than we expect.
Mm-hmm.
And I think this is my last slide on this. So our action can be of this general form with a theta term here, but the presence of this quantum anomaly means there's effectively already a theta term in our action. So again, there's no a priori reason to set theta equals 0 if this term is, allowed in our theory. There are experimental bounds that we've established that Weinberg talks about that basically say the theta term, if it is here, is very small. And here I just mentioned that if you use some instanton analysis techniques, but otherwise hand wave away a lot of details, then the partition function kind of looks like a sum over instanton contributions in a semi-classical approximation with this form. And if you sum over this geometric series, you end up getting a form that has some non-analytic behavior, which I assume is a heuristic way of understanding how there might be a phase transition for very high temperatures between a confinement and deconfinement phase. But
where's the non-analyticity that you're talking about?
If you have a certain parameter g, then this denominator could possibly vanish. If this
right, like g equals square root of 8 pi. Okay. Mm-hmm.
Yeah, if this g gets to be too large, and we know that at high energies, g gets smaller.
Yeah, exactly. So I was actually right in asking about where the analyticity is, or rather the non-analyticity is, because like technically we can't really, experimentally speaking, right? We can't really tune coupling to infinity anyway, right? So
Right, that's fair. So I don't expect, given that this analysis is already super hand wavy, I don't expect us to be able to actually experimentally probe any possible non-analytic behavior in this expression.
Yeah. Mm-hmm.
But that's all I had for this theta term in the chiral anomaly.
Okay, yeah. It's good. It's good. It covers pretty much most of the grounds that we might see in QCD and the chiral anomaly. And I guess one little comment I will make is that the like you mentioned that the theta term, you can write it as a total derivative, and you can basically bring that into a boundary term, right? So the boundary term is on a 3-dimensional manifold,
right?
Because you're integrating over, R4, but like R4 has no boundary, right? But you're saying that this action is trivial. Oh, sorry, it's non-trivial because it is topological. So what is happening here is that like it's exactly the same as in, well, not exactly the same, but analogous to the Aharonov-Bohm effect, right?
Yeah.
Where your gauge field basically acquires a singularity. So in this case, it's a hedgehog instead of like a flux tube. So it's a 3D hedgehog defect. Yeah. So once you acquire that, then your theta term is actually quantized in terms of the monopole charge of your the gauge field A. So if you write down the effective action that describes this topological configuration, you'll find that it's exactly the Chern-Simons action. So it's 8dA plus, I believe it's 3/2 a cubed, right? So if you write down this action in terms of the total derivative, and then you just do integration by parts, and you'll see that the Chern-Simons term pops out, and that describes exactly this hedgehog anomaly.
Right. So,
Mhm.
yeah, if this term is in the action and you do the basic, Euler-Lagrange analysis, and you find gauge fields that satisfy the Euler-Lagrange equations, exactly as you're saying, you can find gauge fields that look like flux tubes that satisfy the classical equations of motion. But the action evaluated at those configurations has this integer winding number dependence times some factors. And
It's important to distinguish between the strong and weak Euler-Lagrange formulation, right? Because if you impose by strong and weak, I mean strong is literally just the pointwise equation, right? So the Euler-Lagrange equation has to be satisfied pointwise. By weak, I mean you integrate it, right? So you impose the stationarity under an integral sign. So that's where the topological anomaly can show up, right? Because if you impose everything, the strong Euler-Lagrange pointwise, if you impose that pointwise, then that forbids all the singularities that can show up, because like you force your gauge fields to be differentiable.
Right.
Yeah. So like that gets rid of like all the interesting stuff that you can have. So technically speaking, you should be like you should impose your dynamics using the weak formulation, which is what people so like that's typically what people do anyways. But it's just some subtlety that you don't see in undergrad variational calculus or whatever. But
yeah, that makes sense. I prefer keeping things in the weak formulation for exactly that reason.
Yeah, I mean, if you look at if you strictly speaking just look at what's the admissible space for the strong Euler-Lagrange equation, you'll see that instantons they're not in that space. So you can't even plug instantons into your strong Euler-Lagrange equation. Right. Even though, at the end of the day, you get 0, but that's away from the instanton singularity. So, by instanton singularity, I mean, the monopole, right? The hedgehog. So
yeah, I mean, if you look at like fluid dynamics books, they basically say that you can get the solutions that look like the weak solutions to the minimization. You can get those solutions from the strong approach via some fancy limiting procedure.
Yeah.
But you kind of have to know what the answer looks like.
Yeah.
In order to do it that way.
Yeah. Technically speaking, you can embed smooth things continuously into the Sobolev space, but the whole point is what the approximation is not going to be unique, right? So the approximation of your weak solution by strong solutions, right? That's not going to be unique. And in topological sectors, in topological sectors, for example, you have and it's labeled by integers. All the instanton weak solutions, they're labeled by integers, so you have infinitely many of them to choose from. So if you're on the torus, then it's just multiplication, but in more general manifolds, you don't have that guarantee. So how you do that approximation, sort of you already have to know which instanton that you want to get at the end, right? So is exactly as you said. So yeah, that's reasonable. but yeah, and also this approximation, the semi-classical approximation, looks very much like a so here basically you're only looking at the gauge fields, right? There are no spinors, no fermions,
Right.
and whatever. Yeah.
Right. I'm only looking at the gauge fields, and I'm just neglecting fluctuations about the instantons.
Yes. Yeah. Exactly. So this is actually rigorous. If you like, believe it or not, this is actually rigorous. Like, given so Witten and Beasley, they have proven this what's called non-Abelian localization, which states that this partition function that you've written down for the Yang-Mills action, so just gauge fields, no spinors or whatever,
Right.
They've proven this. Like, this is exactly correct in a sense that your partition function just localizes around the instantons, and that's all the contributions you get. I'm not sure like what exactly the formula is, but it's exactly this. Like, it's it's a sum of exponential of the instantons, basically.
I think I see
yeah.
where that comes from, because as you're saying, the solutions are very localized around these instanton solutions. In fact, if you try and perturb the instanton solution, because you can't perturb an integer infinitesimally into another integer, I can see how you could say that any field configuration that's perturbed slightly away from an instanton configuration would actually just lead to either a disappearing or an infinite action.
Mm-hmm. Mm-hmm.
I guess an infinite action.
Yeah.
To make sure it doesn't contribute.
So I guess that's more clear in the formalism of the holonomy, right? So if you write everything down in terms of holonomies, you'll see that your Yang-Mills action is literally just a bunch of 1 minus u's and 1 minus v's, where v sort of projects out the topological sectors, or yeah. So in that case, like your Hamiltonian, so to speak, because you're doing a wick rotation, and then once you've imposed the equations of motion, like there's no difference between Lagrangian and Hamiltonian. Don't quote me on that. That's just like that's just me saying stuff. But the point is, like, we're treating this Euclidean action as a Hamiltonian, right? And when you try to minimize it, what's going to happen basically is that, like, around each instanton you sort of have this saddle. Oh, well, not saddle, but like a minimum. Like, it's a true minimum because it's a fixed point in your gauge group, in your structure group. So as you leave it, there's a maximal torus that sort of winds your perturbative contribution around the minimum. So, like, it's not going to be a saddle, okay? It's going to be an actual minimum.
Okay, so it's going to be a minimum, but are you saying
So
it has cusp-like behavior? Like the derivative
exactly.
won't
So
exist?
when you integrate out all the holonomies, right, it doesn't matter if the holonomies is exactly at the saddle. What's that?
Nothing.
Yeah, so the point is, like, when you integrate out all the gauge fields, or if you integrate out all the holonomies or whatever, you'll see that, like, everything around the minimum sort of cancels each other, right? They all cancel each other because because like the maximal torus of your gauge group just drags all the perturbations around in a circle around your instantons. So, like, they all cancel out, and this is called localization of your path integral. And yeah, abelian localization is sort of like, okay, it's good. Like, everybody understands it because, like, in Higgs, for example, right? But for non-abelian localization, you need like there's a lot more subtlety to it, but it's proven. So it's like a sort of a non-abelian gauge theoretic generalization of this Duisterman Duister-Matt Heckman result of localizing like the stationary phase stuff that you see in classical mechanics. So yeah, it's been proven by Witten and Beasley. I can link the paper here.
Sure. I don't think I'll be able to appreciate Witten's work quite yet.
Yeah, but this is just to show that, you know, I'm not talking out of my ass. So
yeah. Sure, go ahead.
So yeah, in case you have like SUN, right? These classical simple groups or whatever over C, you can apply non-abelian localization. And this will get you exactly, well, not exactly, but like a formula that looks very much like this. So it's a sum over the exponential of the instantons.
Right, with the integer
Yeah.
nu or whatever integer you want.
Yeah, that's right. And these instantons are labeled by the irreps of your gauge group. So that's a specific, because Yang-Mills theory, like the theta term, that's a TQFT, right? And it's a gauged TQFT. So like it makes sense that you can, you know, label your instantons in terms of irreps of your theory. So yeah, that is good. And the constant C is like a geometric invariant of your gauge group.
Yeah, I didn't want to write it out.
Yeah. I want to be careful because... Okay, I better not say anything because I don't remember exactly what this constant is, but yeah.
If I recall from Weinberg, it's just some more factors of 8 and pi and other things for this example.
Right. By geometric invariant, I mean like it's just for example, an integer or a rational number that depends on your gauge group, like the representation theory of your gauge group. That's what I mean by geometric invariant. So for the specific case of SU3, right? So that might just be some number that you see. But yeah, what else?
Yeah, if you want, I believe Weinberg sections 22, 23 are where he talks about this. So you can see what he says about this constancy.
Yeah, it's been a while since I read Weinberg, so.
What's Weinberg?
Weinberg is the textbook from which I got
I see.
the info about this chiral quantum anomaly stuff, theta term. So, yeah, I thought it was nice. It's just this whole optional section. I had to kind of grab things from all over the place in Weinberg in order to, coherently put the story together. Whereas, say, in like this PhD thesis by Florian Gruber, she just has it all put together in the correct order, which is great because I found that after I did all the work.
Yeah, it's good. It's a good section.
Yeah, if you want, you might be interested in Florian Gruber's PhD thesis because she basically does topological properties using lattice QCD techniques.
Mm-hmm. I know Gruber. So what?
Practically the end.
Yeah,
the other thing I wanted to sort of mention is that because here you're sort of assuming that you're discretizing into a square lattice, right? But I can pick any other lattice that tiles the plane, like
for the
hexagonal
lattice theory, sure.
Yeah. So I can pick like a tetrahedral tiling, or like a rhomboidal, just any. In 3D, it's even harder because you have like infinitely many sort of these Frank Casper stuff.
You don't even have to do a simple continuation. You could do any tessellation you want.
Yeah. Mm-hmm. Yeah, exactly. But like in the classical case, if we're just dealing with the action itself, then that's completely fine. But I want to bring to attention that how you discretize your space has a major consequence on the quantum theory. Because once you've discretized your lattice, let's just think about Yang Mills, right? Let's just throw away the spinners or whatever. Just on Yang Mills, right? How you assign quantum states to a specific system depends exactly on the graph or the lattice that you assign to that space. So how you color your lattice. So for instance, if we have a square lattice, right? And then I say, okay, I put holonomy here on this edge or holonomy there on that edge. And I sort of join together these edges with the holonomies sort of have this composable property, So you have u mu x, and then you compose it with u mu 1 of x, and you compose it with u mu 2 of x plus mu 1, right? So that makes sure that the holonomies are connected. So if I just join all these colorings together, I get a graph in my space, and my quantum states are labeled by these graphs. Okay, so these graphs, I mean, it's obvious to see that these graphs that you get, they depend very heavily on how you discretize your space, right? Because at the end of the day, if you have a square lattice, you get square graphs, like just a bunch of zigzags, right? But if you have like other discretizations, you can have, weird graphs that sort of becomes non-planar or something. So,
right, like how you discretize your lattice changes, say, how much symmetry you're breaking in the theory in the first place. Like just choosing a discretization in the first place breaks rotational symmetry of your theory,
and translational
symmetry. And so there are people that do things where they choose basically a random discretization or a random tessellation of the lattice, and then they average over these random tessellations in order to try and enforce, like, to bring back the symmetry in an average sense that they're breaking.
I mean, like in terms of just at the classical level, where you're just looking at the actions, right? That's where symmetry breaking is going to manifest, right?
Yeah.
But what I'm saying is that in the quantum theory, where we're dealing with quantum states, right? Like on the classical case, where you look at the action and then you take the continuum limit, like all the symmetries are restored. Like that's the offshot, right? So like in the continuum limit, doesn't matter how you discretize your space, okay? Like you take the limit and then everything's fine, everything's restored. But what I'm saying is that in the quantum theory, right, that's not the case.
Oh, interesting.
Yeah, that's my point. So like how you like people can already see this in 2D, right? So you discretize into a square lattice or into a trigonal lattice, And how you assign like these spins on the vertices and how you assign spins on the edges. I believe it was like there's a specific model. I think it was like some form of key type code that sort of gives you different topological sectors in the continuum limit. So like, yeah, in the quantum theory, that's something that you have to, well, I mean, the topological orders are the same, but how they're arranged by how they're picked out by your choice of the parameters are different, I should say.
Where would I start in reading more about that?
So the first place I saw this was in Debray, Arun Debray. His paper, his PhD paper. Let me just look it up.
Sure. Yeah.
Round TQFT, generalized double semi. Yes. So it's this one. Yeah. So in the first few sections where he mentions that there's this discrepancy of TQFTs in the quantum theory. Yes. Okay. And page 7.
Okay.
Yeah, it's the double semion model. So sort of like, you assign semions to the lattice like just you would do in key type for spins, right? But you have semions instead of spins. So it's like a half key type model basically.
Okay.
But yeah.
I'll look at that.
Paragraph. Mm-hmm. The last paragraph in page 7 talks exactly about what I was saying. That so the CW structure sort of gets you this lattice construction that you have, right? Because each phase of your cube and each vertex and etc., they're all CW cells. So, but how you choose the CW structure, it matters in the quantum theory. So that's the upshot that I want to bring attention to. Like even just looking at topological sectors, right? So who knows what difference it makes in the general QFT setting, right?
Right. I'll have to look at that later.
Mm-hmm.
Thanks.
Yeah, no problem.
Yeah.
I think I've talked enough. So if anybody else have anything else to add, please go ahead. I'm going to shut up.
If not, then I think I'll stop sharing and we'll be done.